Hi students, in the reparametrization concept. So, a given curve can have more than one parametrization. For example, the parabola has a parametrization gamma of t equal to t comma t square. The same parabola y equal to x square can be parametrized like this also. Gamma tilde of t equal to t cube comma t to the power 6. So these two are different as parametrizations because a parametrization is by definition a function, and the value of these two functions gamma and gamma tilde, they are not the same at all the points. So therefore these two are different as far as parametrizations are concerned. However, they have the same image, and the image is precisely the parabola defined by set of all x comma y such that y equal to x square. So one can be treated as a reparametrization of the other. So what is meant, not always but sometimes. So what is meant by a reparametrization? So the formal definition of reparametrization is, suppose we are given a parameterized curve gamma defined on an interval alpha comma beta into Rn. We say gamma tilde, another mapping defined over another interval alpha tilde comma beta tilde to Rn is a reparametrization of gamma if you can go from gamma to gamma tilde and vice versa, from gamma tilde to gamma. So how do you go? So by means of a commutative diagram. So what is that? So this is the given curve gamma. Gamma tilde is said to be a reparametrization of gamma if there exists a bijection phi from alpha tilde beta tilde to alpha comma beta such that this diagram commutes. So what is meant by this diagram commutes? You can start from here, you can reach here and reach here, or you can start from here alpha beta, go here and reach here. Whatever be the way, whether the first way or the second way, the effect is the same. So that is what is meant by the diagram commutes. And one more thing, this bijection phi, it exists such that this diagram commutes. So when there is a bijection, there is an inverse, and you want this phi to be smooth and this inverse, phi inverse also to be smooth. So such kind of parametrizations gamma tilde, they are known as reparametrization of the given curve gamma. So what is meant by this diagram commutes? If t varies in alpha comma beta and if t tilde varies in alpha tilde comma beta tilde, then gamma of t equal to, you start from here, t from here. So phi inverse of t, that will be a point in alpha tilde comma beta tilde, then apply gamma tilde to that, so you can reach here. So gamma tilde of phi inverse of t tilde. So gamma of t equal to gamma tilde of phi inverse of t. Or you can start from here. We can start from a t tilde here. Take phi of t tilde, that will be here. Then take gamma of that means gamma of phi of t tilde. So that is the same as gamma tilde of t tilde. So both the ways you can go. So gamma tilde is said to be a reparametrization of gamma if there is a smooth bijective map phi from alpha tilde beta tilde to alpha beta. It's called reparametrization map, such that the inverse map phi inverse from alpha beta to alpha tilde beta tilde is also smooth. So you want phi inverse also to be smooth, and gamma tilde of t tilde equal to gamma of phi of t tilde for all t tilde belongs to alpha tilde beta tilde. So if that happens, gamma tilde is said to be a reparametrization of gamma. Okay, the next thing is, whenever gamma tilde is a reparametrization of gamma, the other way around is also true. That means gamma is a reparametrization of gamma tilde. That is because you start with the t here, look at gamma of t, so that will be point of R, and that same point can be achieved by traveling like this. So take phi inverse of t, then gamma tilde of that. That means gamma tilde of phi inverse of t. So gamma tilde of phi inverse of t, that is equal to gamma of t for all t in alpha beta. And since phi inverse is smooth, we can treat gamma as a reparametrization of gamma tilde. So they are reparametrizations of each other. Now one more point to note, that two curves that are reparametrizations of each other have the same image, and therefore they should have the same geometric properties, like length are the same. We are going to define a new concept which is called curvature. Curvatures, they are the same, and many such geometric properties hold. They have the same image and so on. We will see an example. The unit circle in R2, namely set of all x comma y such that x square plus y square equal to 1, has the usual parameterization gamma of t equal to cos t comma sin t. Another parameterization is sin t comma cos t, because sin square t plus cos square t is also equal to 1, like cos square t plus sin square t equal to 1. So this is another parameterization. I want you to show that this gamma tilde is a reparameterization of gamma. That means essentially you have to find the reparameterization map phi and draw that commutative diagram. We will go to a definition. A point gamma of t on gamma is called a regular point if the velocity gamma dot t is never 0 at that point. Gamma of t is not equal to 0 at the point gamma of t. Velocity is not equal to 0 at that point. Otherwise, we say gamma of t is a singular point of gamma. And we call the curve regular if all points are regular points. For example, take the parabola y equal to x square. Take the parameterization t comma t square. gamma of t equal to t comma t square. So what is gamma dot t? It is 1 comma 2t. It is never 0 because the x coordinate, the first coordinate is never 0. So this is a regular curve. This parametrization of the parabola is therefore regular. But you take gamma tilde of t equal to t cube comma t to the power 6, then its derivative is gamma tilde dot of t equal to 3t square comma 6t to the power 5, and that is the 0 vector when t equal to 0. Therefore, the origin is a singular point of gamma tilde, namely gamma tilde of t equal to the parabola given by t cube comma t to the power 6. So now we prove a proposition: every reparametrization of a regular curve is regular. Okay. So start with a regular curve gamma and let gamma tilde be a reparametrization. Okay, now go to the diagram which I had shown earlier. So gamma tilde of t tilde equal to gamma of phi of t tilde, this equation. Let us differentiate this. So d gamma tilde divided by d tilde equal to, here you have to use chain rule. So how do you use chain rule? So d gamma tilde divided by d tilde equal to d gamma by dt into dt by dt tilde. So you have to go like this to use chain rule. Okay. So d gamma tilde divided by d tilde equal to d gamma by dt into dt by dt tilde, but dt by dt tilde is the same as d phi by dt tilde, because phi is the function and t is the corresponding dependent variable, and we alternately use this notation. Instead of dy by dx, usually we sometimes denote it by df by dx. So either by the function name or by the dependent variable name we express the numerator. So dt by dt tilde is the same as d phi by dt tilde. Now look at phi inverse composite phi. When you compose it with the inverse, you will get the identity map. So this is the identity map on alpha tilde beta tilde, alpha tilde beta tilde. So by chain rule, again we get d phi inverse by dt into dt by dt tilde equal to 1. But dt by dt tilde is d phi by dt tilde. And derivative, why the right side is equal to 1? Because it is identity mapping here. And what is the derivative of the identity mapping? It is 1. This shows d phi by dt tilde. That means dt by dt tilde. This cannot be equal to 0. Because when this is equal to 0, right side cannot be equal to 1. And gamma is given to be regular, so d gamma by dt, that is the non-zero vector, that's a non-zero vector. So here this is non-zero and this is also non-zero, so the product equal to non-zero. That means d gamma tilde divided by dt tilde is non-zero vector. Therefore gamma tilde is regular. That's the proof. Another proposition is, if gamma of t is a regular curve, that means velocity is never zero, then its arc length s starting at any point of gamma is a smooth function of t. So we have already defined in the previous class what is arc length starting at a point. So how it was defined? It was a function of t, and s of t equal to, recall this was the definition, s of t equal to integral t naught to t norm of gamma dot tau d tau. And by fundamental theorem of calculus, ds by dt is the value of the integrand at the upper limit, namely norm of gamma dot of t. So this is differentiable with the derivative this. Now I have to show that this is a smooth function. So this is a real valued function. A real valued function is smooth if the derivative of all the orders exist and continuous. That is what is meant by smoothness. So I have to show the derivatives of s of all orders, not just the first derivative, all orders exist and continuous. So for simplicity, let us assume that gamma is a plane curve. So gamma of t equal to, let us say, u of t comma v of t. Then gamma dot of t equal to differentiation component wise, so u dot t comma v dot t, and ds by dt equal to norm of gamma dot of t equal to square root of u dot square plus v dot square. Now gamma is a parametrized curve. All parametrized curves are assumed to be smooth. So gamma is smooth, therefore both u and v are smooth. Now gamma is given to be regular, that means u dot square plus v dot square, which is precisely norm of gamma dot of t square, norm of gamma dot of t square, which is square root of u dot square plus v dot square. But velocity is never zero, so norm is always positive. Since gamma is regular, velocity is never zero, that means both these are not zero simultaneously. So sum of the squares is greater than 0. But I have to take the square root here of this quantity. That will be ds by dt. So let us look at the square root function. What about square root function? It is smooth. F of x equal to root x. That is a smooth function of x. Then whenever x is non-negative. So here the situation is like that. Square root of this non-negative number. So you composite this with u comma v going to u dot square plus v dot square. You compose it with f, so what you will get? Square root of u dot square plus v dot square. Both are smooth. U dot square plus v dot square is smooth, f is smooth, so composite is smooth, but composite is precisely this, and this is precisely ds by dt. So what we get? ds by dt is also smooth. That means ds by dt is infinitely differentiable. Therefore s itself is infinitely differentiable, means s is smooth. let us go to another proposition. This is very important. A parameterized curve has a unit speed reparametrization if and only if it is regular. To prove this, assume that gamma is a parameterized curve and it has a unit speed reparametrization, and let it be gamma tilde. I have to show gamma is regular. So let us go back to the commutative diagram to write d gamma tilde divided by d tilde. Yes, so d gamma tilde divided by d tilde equal to, it is d gamma by dt into dt by dt tilde. Okay, d gamma tilde divided by dt tilde equal to d gamma by dt, dt by dt tilde. Now let us take norm on both sides. So norm here equal to, this is a vector and this is a scalar. Usually we write scalar times vector, but here we have written the other way around. So it has the same meaning, scalar times vector. So modulus of the scalar into norm of this vector, that is this. Norm of d gamma tilde divided by dt tilde equal to modulus of dt by dt tilde into norm of d gamma by dt. But since gamma tilde is unit speed, norm of this equal to 1. So therefore each of the terms cannot be 0. That means d gamma divided by dt cannot be 0, or in other words gamma is regular. So this proves one part. Now for the converse, assume that gamma is regular. I have to come up with a unit speed reparametrization of gamma. So assume gamma is regular. How to construct unit speed reparametrization? That is the question. We will try to use arc length as a parameter. That is the idea. So have the arc length given by s of t equal to integral t naught to t norm of gamma dot of tau d tau. Therefore by fundamental theorem of calculus, ds by dt is norm of gamma dot of t, and since this is regular, velocity is never 0, therefore norm is strictly greater than 0. Now derivative is non-zero. Derivative is non-zero. We have learned inverse function theorem in the previous module. So what inverse function theorem says? If the derivative is non-zero, then the function is locally invertible, and the inverse is also smooth. That's what. So from the inverse function theorem, it follows that the function s from alpha comma beta to r, s is the arc length function. This is injective. And its image is an open interval. Why it is open interval? Because continuous image of a connected set is connected. This is connected. So s of alpha comma beta, that is the image of the interval alpha comma beta, that will be another interval. So let it be alpha tilde comma beta tilde. And since it is the image, the function therefore will be surjective also. Therefore, you can look at the inverse map S inverse from alpha tilde beta tilde to alpha comma beta, and the inverse function theorem says that the inverse is also smooth. Okay. So again we are back to the previous diagram I have shown in this page itself. So this is your original interval alpha comma beta, and S is a function from alpha comma beta to alpha tilde comma beta tilde, and S inverse is from alpha tilde beta tilde to alpha comma beta, and you take your S as phi inverse, phi as S inverse. From here to here you have S inverse, and from here to here you have S. So you take the reparametrization phi as S inverse, and let gamma tilde be the corresponding reparametrization of gamma. That means this diagram commutes so that gamma tilde of S equal to gamma of t. So here S varies. I will use the notation S instead of t tilde, because here the image points are denoted by S equal to S of t, where t in alpha comma beta. So this variable here is S. So gamma tilde of S equal to gamma of t, where what is t? It is phi of S. Okay. Let us use chain rule. So d gamma by dt equal to, you can go like this and go like this. So that is chain rule. So d gamma tilde divided by ds into ds by dt. D gamma tilde divided by ds into ds by dt equal to d gamma by dt. Let us take norm on both sides. So norm of d gamma tilde divided by ds into modulus of ds by dt equal to norm of d gamma by dt. But ds by dt, that is positive. ds by dt is positive. So modulus of ds by dt is the same as ds by dt. And norm of d gamma by dt, that is the same as ds by dt, because this is gamma dot. ds by dt is gamma dot. Right? So you can cancel this and this, because they are non-negative, and you can conclude that norm of d gamma tilde divided by ds is equal to 1. So gamma tilde, when you parameterize with respect to the arc length S, you will get unit speed curve. Gamma, when you parameterize with respect to S, call it gamma tilde, you are essentially getting gamma tilde is unit speed. So the conclusion is, parameterization with respect to arc length, S, will give unit speed reparameterization, provided the given curve is regular. Okay. Let us prove a corollary to this. So for a regular curve, unit speed reparameterizations exist. Let gamma be a regular curve and gamma tilde be a unit speed reparameterization of gamma. given by gamma tilde of u of t equal to gamma of t for all t. So u is the parameter here for gamma tilde. Suppose there is some other way in which you can produce unit speed reparameterizations. We have seen one method, it is using arc length. Suppose there is another way. Using some another variable u, you can reparameterize your gamma and get another unit speed reparameterization gamma tilde of gamma. Then what can you conclude? Is this u related to your arc length? Yes. That is the question. So that is what this corollary says. Then if yes is the arc length of gamma starting at any point, we must have u equal to plus or minus s plus c, where c is a constant. So this is the only way you can produce unit speed reparameterizations. Essentially it will depend upon s. Any such unit speed reparameterization is related to s in this way. It is given by plus or minus s plus some constant c. And the converse is also true. If u is given like this, then you parameterize gamma with respect to u, essentially you will get a unit speed reparameterization of gamma. So how do we prove this? You have this equation, you differentiate both sides using chain rule. In the left side you will get d gamma tilde divided by du into du by dt equal to d gamma by dt. Now take norm both sides, you will get norm of this into modulus of this equal to norm of the right side, d gamma by dt. But this is precisely ds by dt. Okay? But gamma tilde, it's a unit speed reparameterization of gamma. So this is equal to 1. So 1 into modulus of du by dt equal to ds by dt. 1 into modulus of du by dt equal to ds by dt, where this is always non-negative. So du by dt, that may be negative, we don't know. So how do I solve this? Modulus of du by dt equal to ds by dt means du by dt equal to plus or minus ds by dt. Du by dt equal to plus or minus ds by dt. Integrate with respect to t, you will get u equal to plus or minus s plus a constant of integration c. So we have proved one part. Converse also we have to prove. Conversely, suppose u is given like this, I have to show u will give rise to a unit speed reparameterization. What is du by ds? It is plus or minus 1, and d gamma tilde by du is from here, or d gamma tilde divided by du into du by dt equal to d gamma by dt I want you to prove this, complete the proof of this part. Maybe you have to write the other way around for the chain rule and conclude. Thank you.